Hey SM2, this is an additional video for 4.1 because I forgot to cover it when we first went over 4.1. So I need to cover this. Make sure you watch this video, fill out the notes. This stuff will be on the test, so make sure you know it. So first of all is like radicals. Um, So we're going to talk about what like radicals are. So specifically, we're learning today how to add and subtract, how to add and subtract radicals. Because last time in 4.1, we learned how to divide and multiply. um, so for multiplication, there is a product property where you could take the square root of a times the square root of b, or more specifically, or more generally, you could take the nth root of a and the nth root of b, and this is equivalent to the nth root of a times by b. Or you could take the nth root of a divided by b, which is equal to the nth root of a divided by the nth root of b. So whenever you do this, you can see that you can just split it up if it's having to do with these things. But you can't do the same with adding or subtraction. So the nth root of a minus the nth root of b, you can't combine this to be the nth root of a minus b. It doesn't work that way. Or with addition, you can't do the same thing with addition. And then you can't do the nth root of a minus b, minus b, and you can't separate this to be the nth root of a plus or minus the nth root of b. So addition and subtraction doesn't work the same way. So to add and subtract, you need to have what's called a like radical. So to talk about what a like radical is, let's talk about the nth root of a. So we know that this right here, we talked about it before, is called the index number. This is the index number. This right here is called the radicand, and this of course is the radical. Now, so a like radical is whenever two radicals, or I guess we should say two or more radicals, when two or more radicals share the same index number, and radicand. So, for example 8a, in order to add, so we have three different radicals. Now, this radical right here has an index number of 2 and a radicand of 11. This has an index number of 2 and a radicand of 7. This one has an index number 2 and a radicand of 7. Now, the coefficient in front of the radicals right here, one is 8 and one is 5 and one is negative 8. But in order to add like radicals, or in order to be like radicals, it doesn't say anything about the coefficient. They just have to have the same radicand and index number. So if you have like radicals, you can add and subtract them. Much like the idea of, let's say if we had 5x, like instead of having 7, let's say we had a square root of 7, let's say we just had 5x. And then right here we had minus 8x. Well, we can combine these terms because they are alike, and this would be negative 3x. So similarly, we can do the same thing with like radicals. We can add and subtract like radicals. So, because these are like radicals, I can combine them, so this would be equal to 3 square root of 7 plus the square root of 11. And we can't do anything with the square root of 11. There are no other radicals like it, so that would be the solution right there. You could also look at it this way. So let's take these two like radicals. So 5 square root of 7, this is the same thing as 5 times square root of 7, which would be equal to square root of 7 plus the 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 square root of 7. So this is the square root of 7, 1, 2, 3, 4, 5. So we have 5 square root of 7s. That's what this is saying right here, 5 square root of 7s. So then in here, if we have 5 square root of 7s and negative 8 square root of 7s, when you add them together, you'll have negative 3 square root of 7s. Alright, let's try B. So here you can see that we do not have like radicals. This is a radicand of 5 and a radicand of 20, so we can't add them. But the goal with radicals is to make sure that the radicand inside is as small as it can be. So I'm going to simplify this right here. I know that the square root of 20 is 5 times by 4. And I can change this to be, or I guess more specifically, I could write this to be the square root of 4 times by 5. And using the product property, this is the square root of 4 times the square root of 5. So then this is going to be 2 square root of 5. So I have 10 square root of 5 plus 2 square root of 5. I simplified this to be 2 square root of 5. So if I have 10 square root of 5 plus 2 square root of 5, I can add the coefficients, and this is 2 square root of 5. 12 square root of 5, sorry. And that's that. Now for C, I have 6 cube root of x plus 2 cube root of x. Because I have the same radicand and the same index number, I can add the coefficients. So this will just be 8 cube root of x. Okay. Now going on to example 9, we're going to simplify, and we have to use a little bit of multiplication. So there are two methods that we could go about this. So first method, what I'm going to do is I'm going to try and simplify. Well, first I guess what I could do is multiply, distribute. So I have this square root of 5 out here, so I can distribute it to both terms inside the parentheses. So square root of 5 times the square root of 3 would be the square root of 5 times square root of 3 minus the square root of 5 times the square root of 75. So I'm just distributing this and multiplying it to both of these terms inside. Now, square root of 5 times the square root of 3, because it's multiplication, I can combine, or I can multiply the radicands together. So this would be the square root of 15. Now I could do the same thing on the right side, but I want to make sure that this right here, the square root of 75, is that the radicand is as simplified as possible. So I'm going to simplify this. So I still have minus square root of 5, but now I'm going to do minus the square root of 25 times by 3, because 75 is 25 times by 3. So I have the square root of 15 minus the square root of 5, and now I have times the square root of 25 times the square root of 3. So this is the product property. So I have the square root of 15 minus the square root of 5 times by 5, because square root of 25 is 5, times by the square root of 3. So now here, these terms are all being multiplied, so the order of multiplication doesn't matter. So I'm going to rewrite this to be the square root of 15 minus 5 times the square root of 15 times the square root of 3. And because these are being multiplied, I can use the product property, and this will be the square root of 15. So now I have square root of 15 minus 5 square root of 15. So here I have 1 square root of 15 minus 5 square root of 15s. These are like radicals, so I can combine their coefficients, so 1 minus 5 would be negative 4 and square root of 15. Okay, so this was a method of distributing first. Now, for the second method, what I'm going to do is I'm going to simplify first. So I'm going to simplify the square root of 75 first. So I have the square root of 5 times the square root of 3 minus the square root of 25 times by 3. Now, so this is equal to the square root of 5 times the square root of 3 minus the square root of 25 times the square root of 3. That's by the product property. I can split those up. So this is equal to the square root of 5 times the square root of 3 minus 5 square root of 3. Because square root of 25 is 5. Alright, now I have the square root of 5 times by, so here I have like terms. I have 1 square root of 3 and minus 5 square root of 3. So I can combine them to be negative 4 square root of 3. Alright, so now I have square root of 5 times by negative 4 square root of, times by square root of 3. Again, this is all just being multiplied by one another. So order of multiplication doesn't matter, so I can change this to be negative 4 times the square root of 5 times the square root of 3. And using the product property, I have negative 4 square root of 15. So you see that no matter which way we do it, we still get the same answer. So this is a method of simplifying first. Okay. Alright. So that should be pretty much it for the rest of 4.1. Now, there is a review posted online on Canvas, and I want you guys to make sure that you cover this, but if you go to the review for exercises 22 through 27, there are these type of problems. So if you want, you can watch this and I'll go through these. I'll go through them fairly fast, but you can go back, pause, and rewind to make sure you can follow along. But I'm going to simplify these. So I have the square root of 3 square root of 8 plus 3 square root of 12. These are not like radicals, so the question is, can I simplify one of them? So here, this could be 3 square root of 4 times 2, because 8 is 4 times 2. Now I can use the product property to be the square root of 4 times the square root of 2 plus 3 square root of 2. Square root of 4 is 2. So then this is 6 square root of 2 plus 3 square root of 2. So when you add, now that these are like radicals, I can combine them, and now it's 9 square root of 2. So 6 plus 3, which is 9. Okay, let's see what's another good one. Let's try 25. So, let's, on this one, so since we have a binomial here, let's distribute this inside. So I have 2 times the square root of 5, now it's timesing by the square root of 6, plus 2 square root of 5 times by 2. Now order of multiplication doesn't matter, so for this part right here, I'm going to do 2 times the square root of 20. Or, no, sorry, times the square root of 30. Because 5 times 6 is 30. And then for the second term, I'm going to multiply these two together, so it's going to be 4 square root of 5. Now, can I simplify the square root of 30? So let's see, if I take 30, let's take its factors. So you can have 2 and 15. 15 can be split up into 5 times by 3. Okay. So it doesn't look like it has any factors that you can take the square root of. So that's just going to be 2 square root of 30, and then we have plus 4 square root of 5. So since we can't simplify that anymore, because we can't take any factors of square root of 30, and then square root of 5 is just the square root of 5, so these won't be able to combine. We can't get any like terms or like radicals out of that. And to end, let's do number 26. So for number 26, here I have two binomials, so this might look familiar. So for example, let's say I had x plus 2 times by x plus 2. Now whenever I would do this, I would have to FOIL, if you guys remember doing that. Now, so I'm going to treat this the same way. So I have to take this square root of 7 and multiply it by both of these terms right here. So I have the square root of 7 times the square root of 7 plus square root of 7 times the square root of 3. Now I have to take this term, multiply it by both of these terms. So then I have minus square root of 3 times square root of 7. And then I'll have, so I have negative square root of 3 times by positive square root of 3. So it's going to be minus square root of 3 times the square root of 3. So let's go ahead and do this. So because these are being multiplied, this is going to be the square root of 49 plus square root of 21. This is going to be minus square root of 21, and then minus square root of 9. Now I can simplify. So square root of 49 is equal to 7. So you notice here that this is positive square root of 21, this is negative square root of 21. So those will cancel. And then I have minus square root of 9 is equal to 3. So here I have 7 minus 3. So this will just be equal to 4. Okay. Might do some more example problems, because one thing that we didn't really talk about was factoring, or taking the square root with prime factorization. So I'll explain what that is here. So prime factorization, so let's use an example. Let's do number 3 as an example. So prime factorization means that you're trying to find all the prime factors that make up a number. So in this case, 162. So if I take 162 and I'm going to start writing out its factors. So I can take 162 and divide that by 2. If I do that, I get 2 times 81. 2 is a prime factor. So 2 is prime, and it's a factor, so it's a prime factor, so I'm going to circle all my prime factors. Now 81 isn't prime, so I can still divide 81. I think I can divide that by 9, so factors of 81 are 9 times 9. Now these still are not prime factors, but I know that 9 has factors of 3 and 3, and 3 is prime. So here I have more prime factors. So these are all the prime factors that make up 62. So if I were to do 3 times 3 times 3 times 3 times 2, I would get 162. So I'm going to rewrite my square root to be 2 times 3 times 3 times 3 times 3. And then for g to the 6th power, I'm going to write this as g squared times g squared times g squared. Or better yet, I'm going to rewrite it as g cubed times g cubed. So you agree that g to the 6th power is the same thing as g cubed times g cubed. Okay, So I've broken down all of this to be what's underneath this radical. So now I'm going to do what's called grouping. It's like taking the square root by grouping. Now this is a square root, which means I'm looking for groups of 2. Okay, so if I can group like terms into groups of 2, I can factor that out. So here I have a group of 3 and a group of 3 right here. And here I have a group of g cubed. So what this means is I can take out a 3, another 3, and a g cubed. So on the outside of the radical, I have 3 times by 3 times by g cubed. So I just removed these from the radical. So inside, I only have the square root of 2. And then on the outside, I can simplify to be 9g cubed square root of 2. So again, what I did was used prime factors and grouping in order to take the square root. Let's say, number 12. This will be another good example. So, using the quotient rule, because they're all under the same radical, using the quotient rule, this could be the cube root of 12a to the 6th power divided by the cube root of 512b to the 4th power. Now what I'm going to do is I'm going to break these up and do prime factorization. So for 12, so I'm going to start with the numerator and I'll go on to the denominator, but for 12 I can break this up to be 2 times 6, and then 6 I can break up to be 2 times 3. Now these are all the prime factors. So here I have the cube root of 2 times 2 times 3 times by a squared times by a squared times by a squared. Another way I could do this, if it makes a little bit more sense, is I could do the cube root of 2 times 2 times 3 times a times a times a times a times a times a. So a 6 times, right? That's going to give me a to the 6th. Now, this is a cubed root, so I'm looking for groups of 3. So here's a group of 3 of a's, here's another group, and that's it. I can't group anything because there's not another 3, or there's not another 2, and there aren't 2 other 3's. So I can simplify this. I can pull out an a and an a. So then I have a times by a times the square root of 12. I'm just going to leave that as the square root of 12, or the cube root of 12, sorry, which means I can no longer simplify that. I can't simplify the cube root of 12. But this ends up being a squared, right? I guess I'll write this down further, but now let's try the denominator. So I have 512. So for 512 in the denominator, I want to find the prime factors. So I know that I can divide this by 2 because it ends in a 2, therefore it's divisible by 2. So 512 divided by 2 is 256. 256 can be divided by 2. So this could be 2 times 128. Again, remember that we're circling our prime factors. 128 divided by 2 is 64, so this is 2 times 64. 64 divided by 2 is 32, so 2 and 32. This is 2 and 16. This is 2 and 8. 2 and 4. 2 and 2. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's going to be quite a lot. So I have the cube root of 2 times 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 2. And then b to the 4th power. So let's look for groups of 3. because it's a cube root. So here's a group of 3, here's a group of 3, and here's a group of 3. So I can pull out 2 3's. So this is equal to 2 times 2 times 2 times the cube root of b times b times b times b, which is b to the 4th. So I still have the cube root of b times b times b times b. So this is equal to 8, because 2 times 2 times 2 is 8. Cube root of b times b times b times b. Cube root. So I'm looking for groups of 3 still. So here is a group of 3, so I can pull out a b. So it's equal to a times by b, the cube root of b. Okay, so I've simplified the denominator, so my answer on the top will be a squared cubed root of 12 divided by 8b cube root of b. Okay, so that's what prime factorization is, and that's how you can use it to take cube roots and square roots. But anyways, that should be a good enough practice for the test. Again, make sure that you do all of this review, as well as reviewing how to use a quadratic formula from 2.5. But if you can complete this review confidently, and if you can handle 2.5, you should be in good shape to take the test. Alright, but let me know if you have any questions, and I'll talk to you guys later.